guess I just feel like I'm the same way too. I guess I just feel like good things are gone, and the weight of my worries is too much to take on. I think I remember this dream that I had. This love's gonna save us from a world that's gone mad. I guess I just feel like what happened to that? I guess I just feel like the joke's getting old. The future is fading, and the past is on hold. But I know that I'm open, and I know that I'm free. And I'll always let hope in wherever I be. And if I go blind, I'll still find my way. I guess I just felt like giving up today. Thank you very much. I guess I just feel like I guess I just feel like nobody's honest, nobody's true. Everyone's lying to make it on through. I guess I just feel like I'm the same way.
Good afternoon. Welcome to CSE141's third lecture on memories again. And today we are going to continue our discussion on memory. But before we start, it's always great to have you guys remembering like where we are from to bring something back into your memory. So again, why we are here is because von Neumann architecture, it contains processor, memory, storage, and processor and memory. They are actually the most important part when you are running the program. And we have been talking about processor the whole time before the midterm, and right now it's the time for memory. So what's the issue with memory? Instead of just, we saw that memory is just like giving the processor whatever it needs, and there shouldn't be too much of an issue in memory. However, here's the big issue. The performance gap between the processor and memory is increasingly significant because for processors, we try to use the improvement of process technology to improve the clock rate. However, for memory, we focus on improving the capacity. So turns out our solution right now is that, well, we just build a hierarchical memory. So instead of like building a big, giant, fast memory, we build we put a small amount of faster memory nearby the processor, and gradually, as we increase the size, the memory is going to be slower, so we can maintain the cost properly. So it turns out that this is what you see in your memory hierarchy. Roughly, you have processor, you have cache, you have DRAM, you also have the storage. However, within the SRAM cache, you have L1 cache, L2 cache, L3 cache, right? So that's why that's the memory hierarchy looks like. And when we access the cache, first of all, you receive the load store instructions from your processor, and for the processor, how they distinguish the data you need is using the memory address. And in a cache, we structure the cache in a way that is set associativity. It means that when we want to look up the cache, we don't go through all the blocks. Instead, we just go to a small set of blocks that contains your, that potentially would contain your data. And which set should I go to? That's like a hash function. And how we do that is that, how we do this hash function is that we partition the memory address, and the least significant of the memory address, they are the block offset. Means that if the data indeed exists in a cache, where within a cache block can I find it? So the very first stage is, and the second part is the set index. It tells us, it's actually the hash, where the hash value is, right? It tells you where in the set of the cache can you potentially find a block if it's already there. And then the text serves as the identifier of your data. So for this given address, the block offset is 4. So we know if the data exists in the cache, the multiplexer should select the fourth word, or say the fourth byte, starting from the fourth byte in the block as the data we want to output. And use the set index. We go to the set may contain our data, and then we use the tag to compare if the data block is indeed there. And for this example, we can find 1, 0 on the left-hand side. So it's a hit. And when it's a hit, we just use the box to select the word that we are going to output. So that's the basic concept of the cache access. However, there are a few more operations that we need to do. So first of all, when you are reading data, you issue a load instruction. And again, we partition the address into tag, index, and offset for lookup. And if it's already there, then we just consider this is a hit. We directly return the data to the processor core. And if this is a cache hit, and if it's a level 1 cache, and if your level 1 cache speed is aligned with your processor speed, this cache hit usually would not cause any additional penalty. However, if the data is not in your L1, first of all, because our cache require the data to be always present, we require the L1 cache to be the one who should who is the one who would interact with the processor. So you really need the L1 to have the data block that you are requesting. So in this way, we have to request a data block from the lower level memory hierarchy. However, there might be a chance that my cache is full. And when I full, I need to kick out some block. And if unfortunately this block is dirty, meaning that previously it has been modified by your code, then you have to write it back first. And then you fetch and then you can finally try to fetch the block from the lower level memory hierarchy. However, there is still a chance that it's not there. So you have to write back again if the selected victim block to accommodate the incoming block is dirty. And then fetch the data again from the lower level memory hierarchy, put it into the space that you already allocated for him for the data block, and all the way back to the processor core. And if it's right, there's nothing too different except for the fact that we have to write and set dirty in L1 if it's a hit. However, if it's a miss, again, write back, fetch block, and return the block and set dirty in the L1. Okay, so a lot of you might be curious about, okay, I know I want to partition my address, But how do I know how many bits in each field? So my formula is C equal to ABS, which is probably the easiest formula that you can use to derive these answers. So memorize this. This is so for this class, we don't ask you to memorize too many things. However, C equal to ABS. Every of my students who pass the class should know this. So the C equal to ABS means that the C is the capacity, A is the weight associativity, B is the block size, S is the number of sets. And most of the time, you are only given three out of the 4. And the number of bits within a block. So you should use the knowns to resolve those unknowns. And if you want to know how many bits do I need in a block offset, usually it's log. You have to do it through log 2b. And the reason is because thinking about why you need block offset, because you want to pick the byte, the word that you want within a block. So that's related to the block size. And the number of bits in set index is log S, because that's the number of bits required to figure out which set should you go to. So it's related to number of sets. And the remaining bits, they are the tag bits. So that's the whole picture of C equal to ABS. And with that, you know, like, okay, if I'm given a memory address like this in a processor like AMD's processor, then these are the number of bits should be in offset. These are the number of bits should be in index. So I can partition the address like this. And in a very beginning, nothing there. So it's a miss. And then, well, again, we first time touch B0. So it must be a miss. And however, this time when we try to store C, we need to accommodate C into index 0. However, remember the meaning of two-way set associativity is that for each index, you can only have 2 blocks concurrently. So it means that right now you have 4 and 6, you have to kick out 1. So the usual policy we use is the LRU policy, which we kick out the least recently used one. And in this case, it's definitely the fourth. So we serve this miss, we evict the fourth. However, the consequences is that if you keep going, you will find out this cache performed terribly for the code. And another company called Intel, for the same pieces of code, because their memory architecture, their cache design is better. So you can see for these pieces of code, their hit rate is really high comparing against the 0 hit rate in AMD's processor. So that's what we learned from the last lecture. And today we are going to talk about why there are cache misses and what are the remedies for cache misses. All right, so I kind of like reveal why we see those misses, right? So there are 3 big categories of cache misses that you have to you can look and see. And the reason why we are so keen about identifying the source of cache misses is because we are engineers. We want to solve problems, but before you can solve problems, you have to figure out why there is such a problem. And the 3 C's here is to tell you why. So the first type of miss is called compulsory miss. So it's the cold start miss, first time access to a block. So the very first time you access to a block, it must be a miss. So for example, if I ask you guys to do reading quiz before the lecture, and if you never read the reading quiz, right, then it means that you never know the block of content in the class into your brain. So no matter whatever poll question I ask you, there's highly possible you are going to answer it incorrectly. So that's some kind of compulsory miss because you never read the content, you never try to load this block into your brain. So the same thing for the processor, for the cache. If that's the content that the application never tried to use before, there's no reason why the cache should contain that content, because as you can see from the previous slides, the cache fills the content on demand. Only if there is a load store instruction, there is going to be a chance that the cache is going to fill those blocks, right? So if there's no load store for a specific block or an address within a specific block, it's not going to happen, right? So compulsory miss is the first time miss. So the very first time your application sees it, it's a miss. The second type of miss is the capacity miss. So saying that if I give you like 3 books in computer architecture for your final, then it's very impossible. It's highly impossible for you guys to like memorize everything and in your brain. And so because you have limited capacity, although I know you have more potential than 3 books, but let's say 3 books, right? And don't thinking about that I'm insulting you, because you know I have trouble with more than 2 books, right? So saying that your brain is limited, right? So the same thing for your hardware, right? Your hardware has limited cache size. So there's definitely going to be there's sometimes a case that if your application is going to access huge amount of memory, then you just cannot accommodate everything in your cache. So that's going to have capacity misses. And the last type of miss is called conflict miss. So it's occurred because your data is replaced by another block that maps to the same set. So it's similar to the case of hash, right? So so these are the 3 types. And for conflict misses, it means it's the case that, well, it's the case that, well, my cache has capacity. However, just because you have set associativity, and just because your set can only contain 2 blocks, so it's going to be a miss. So that's the case for a conflict miss. All right, so let's look at the early example that we had in a direct map cache. So right now, if we look at this one, right? So I want to invite some of you to go through this example again with me and tell me what type of miss are we going to interact when we are accessing the cache. So can I have some of you raise your hand? Otherwise, I would randomly select 1 people. All right, no one wants to save the class. Okay. All right, so I have Yizi. You are the hero last class. So why don't you try to be the first hero of the day? You are supposed to be unmuted.
Hi.
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 Yeah.
Sorry.
So for the very first access, hit or miss.
Wait, sorry, I can't hear that.
Okay, so can you hear me now? For this address, hit or miss.
Wait, what?
For this address, for this memory access, hit or miss.
Yeah.
Hit or miss.
It's a miss.
And what type of miss?
I think it's a compulsory miss.
Why?
Because it's the first time, like you have to miss one before you.
Right, you got it. Right. How about the second one, hit or miss?
The second one is a hit because you're like, yeah, you access that.
And how about the third one?
The third one?
Mm-hmm.
The third one is I think it's hit.
Why?
So
which set should I go to look in the cache?
Because the set with the index 1.
Right, and what's in there?
Oh, it's nothing there, so it's compulsory miss too.
It's compulsory miss, right? Yeah. How about the next one?
The next one is it's a hit.
It's a hit, right? And how about the next one?
It's compulsory miss.
It's compulsory miss, right? Because this is the first time we see this block, right? So right now we replace the content with 1 here, right?
Yeah.
And how about the next one? Hit or miss?
One, it's a it's a hit.
It's a hit. This one?
It's a hit again.
How about this one?
This one is hit.
This one?
I think it's hit.
Why is a hit? What's
because
in there?
It's 40 in there. And so we have I think it's a hit because we have the tag of 10 and the index of just 1 before.
But it's gone when you are accessing this one, right?
Oh, yeah, yeah. True.
Right, look at the left-hand side, right? So is it a
Oh,
hit
right.
or miss?
Yeah, it's a miss because we can't find anything that
But
matches.
what kind of miss is that?
Um, it must be like wait. It's a It's a collision miss.
It's a conflict miss,
Okay.
right?
Conf- yeah.
So is there any capacity miss here? No, because we still have quite a lot of space to use, right?
Yeah.
Okay, so do you want to try one more run for the two-way cache?
Um, maybe not. I don't know about this one. The two-way.
Oh, really? Well, you can just partition the address like this, right? Do you
Yeah.
feel more confident now?
Yeah, I can try.
Okay, so for the first access, what type
For
of hit miss or is a hit?
It's a compulsory miss. First.
Okay, it's a compulsory miss. So at this time, we need to put this block inside the cache, right?
Yeah.
And how about the next access, hit or
The
miss?
next, it's a hit.
It's a hit because if you go to index 0, it's here, right?
Yeah.
And how about this one? How about the third one?
The third one, it's a compulsory miss.
It's a compulsory miss. How about the fourth?
The fourth, it's hit.
It's hit, right? And because at this moment, we already put 11100 there, right? And how
Yeah.
about this one?
This one is a compulsory miss.
It's a compulsory miss because this is the first time we have it, right? And right now we are going to find a place to put in 110, but fortunately, because this is a two-way set, so if you go to set 1, there is another place that we can place this one, right?
Yeah.
Okay, now hit this one.
This one it's a hit.
It's a hit, right? And previously, do you remember what was it?
So previously it was 0 1 0
Yeah,
0.
but in the previous cache, right? For this
Yeah.
this data address, is it a hit or a miss in the previous configuration, cache configuration?
It was a miss.
It was what type of miss?
It was a compulsory.
No, it was a conflict miss,
It's
right? But now it's gone, right?
Yeah. Yeah.
Okay, so that's the difference between two-way and direct map cache, right? So after you walk through this, I think I want all of you to look at this example again. I want to specifically ask you about how many of the cache misses here are conflict misses. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at your answers. I just figured out that, every time when I saw C is the most popular answer, it means that you guys are just guessing, right? So why don't you go ahead and discuss with your friend within 2 to 3 minutes, and I already sent out the invite to through the group through the chat. So please do it. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so things does change a lot after discussion. So I do want to invite some of you to share your personal experience with us and how does that change your mind? Okay, I have Kashyap.
Hi, so our group thought that the answer was D,
Mm-hmm.
and it was because the cache from the previous lecture, we remember that the cache misses 100% of the time.
Right.
And
so if you don't mind, go through that with me again, right? So for this one, right, this is what type of miss?
The first time it's a compulsory miss.
Okay, so how about this one?
Compulsory.
Compulsory, right? How about this one?
Compulsory.
Compulsory, because this is the first time we access C, right? But how about this one?
This time it's a conflict miss.
It's a conflict, right? So if you keep iterating, right, the rest of them, they are going to be conflict miss, right? And the next time you are going to meet compulsory miss are those, right?
Right.
So you are only going to have compulsory miss once per 16 times. It also means the rest of them are conflict misses, right? Okay, yeah. Thanks a lot for your insights in your group's insights. Right, so if you look at this, right, it's 100% miss rate. However, the conflict misses here, they are actually 93%, 93.75%. All right, so let's look at the Intel Core i7 processor, and let's retry the same question again with Intel processor and see what's the main source of misses in Intel processor. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. So surprisingly, every answer has its own advocator. So look at this. We definitely need some kind of group discussion. I already sent out the screenshot through the chat. So why don't you go ahead and start discussing with your group. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, after discussion, the distribution doesn't change that much. The only loser is D. So can I have some of you share your thoughts with me. Like, why do you think your answer is that? Okay, so I have Kashyap.
Hi. So our group thought that it was E
It was
because,
E. Okay.
yeah. So no blocks in the execution get evicted, and every time a new block is loaded is just when we no longer need to access the 16
Right.
byte
So
block.
if you iterate this table, right, if you just throw the table, you'll figure out all misses here, they are compulsory misses, right? All
Yeah.
misses here, they are compulsory misses, right? So because all cache misses are compulsory misses. And what the question is this about? How many of the cache misses are compulsory misses? 100%.
Right.
All right. So next time when you answer this question, be careful about the wording. All right. And thanks a lot. And thanks to your group's insight. So so right now we know there are 3 different types of cache misses. Now, as I mentioned, the reason why we want to know this is because we want to improve it. So how to improve 3 different types of misses? And I know you already seen some examples, and you can probably think about how to do it. And the first type of approach improves 3, and you already seen like the influence of cache configurations on AMD processor and Intel processors. So right now, think about this examples that we have seen so far. Can you identify the configuration of A, B, C's and their relation with 3 C's? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, again, C is the most popular answer, but I know you guys when you guys chose C, it's just a guess. So why don't you go ahead, discuss with your friend. Let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so looks like you guys are converged to either C or D. So can I have some of you share your thoughts about this question? Okay, so I have David. And I also have Kashyap. Okay, so why don't you guys both share?
Okay. I hit C, and I thought that the correct ones are 1 and 3.
1 and 3. Okay, how do you know the first one is correct?
Well, based on the previous examples, we see that when you allow more blocks to go to one tag, then there will be
one set, right?
Yeah, for one set. Then there will be less conflict.
Okay, and how about the third?
Well, I think increase the block size usually decreases the okay, I'll just say this. You have to upload more data. I think every
okay, great, right? So
yeah.
there is an overhead in fetching the data blocks, right? So when you access the data with larger data blocks, it's going to increase the time and in getting the data from a lower level memory hierarchy, and that's indeed what the miss penalty is about, right? Kashyap, any other thoughts?
So I agree with 1 and 3 being correct, but I'm not really sure about 4.
Okay, what do you think?
So for example, in the case with the Intel processor, if we increase the block size to about, let's say, 128 bytes, then the number of compulsory misses would be less.
Right, so you got it, right? So for this example, right, if we make the block even larger, right, so the index, it will still be index 0 here, right? So we are not seeing compulsory misses. Instead, we will see hits here, right? So actually the answer to this question, I would say it's 3, in a way that, okay, and thanks both of you. I think your insights are really great. And what I would see here is that, you know, first of all, right, the increase, well, no one agreed with this because you know that increased associativity, we would need more mocks, need a comparison of your text, meaning that it's going to be longer. So the hit time is going to be longer, right? And for the block size, because you have to fetch more data during each miss, so the miss penalty is higher. And for block size, if you increase it, on the other hand, because you bring more data into the cache, so you reduce the chance of compulsory misses. So for this question, I would say 3 of them will be correct. All right, so this is the summary of how we can improve 3Cs. However, this is computer architecture class in CSE department. So there are more things you guys can do. And as I mentioned, programmer is basically the most important factor in computer systems. So today I'm going to show you how important are you in the application performance that's regarding memory. So the first thing that we learned previously in instruction set architecture is the memory addressing alignment. So you had the question in a midterm regarding like how big a data structure is, and you know for aligned access you must need your data structure, your instruction, your variable to be aligned with the size of your data structure. So if you didn't align it properly, you are going to miss memory space. And again, if you are consuming more memory space and you are actually increase the case of cache misses because you are not using your cache capacity wisely, and you are going to increase the chance of capacity misses, right? Another thing is thinking about this. What's the right data structure, right way of structuring your data? So this example shows you that, well, if I want to, say I want to create a system like Canvas, right? I could either create a data structure for each student, or I can create a data structure for the whole class. So the left-hand side is a case that we are creating an object for each student, and for the class is an array of objects, right? So if you want to calculate the average of each homework for the whole class, this is the pieces of a code that you are going to write. And your data layout inside your memory, more like this, right? You have the ID of the first student, the homework for the first student, the average for the first student, and then go to the second student. Another type is called object of arrays. So instead of like considering each student as a single object, we consider the whole class as a single object. And the object itself is actually a combination of arrays. So the whole class is like a big table, and the big table would be like, I have a table for ID, I have a table for homework, I have a table for average, and as we know, we want to in favor of the layout. So the ID itself is a consecutive array, as you can see here. The homework here is a consecutive array, as you can see here, and the average here is another consecutive array. So if I want to calculate the average of each homework, the code would be like this. So right now I want to ask you, for this two data structure, which one would be faster if the purpose is going to ask you compute the average grades of each homework? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like it's worth a while to have a group discussion, and I already sent out the screenshot to the group. So why don't you go ahead and discuss with your friend really quick. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, now B is the dominant answer. So can I have some of you share your thoughts? By the way, one more thing that I want to mention is that I saw some of you didn't go into the breakout room instead. You just click. I believe you are probably thinking about like in the way you will not miss the participation grade, but not going to the discussion. So next time, if I start a group breakout room and if you didn't join within 15 seconds, I will take a screenshot and I will withdraw all your participation grades. All right, so right now I need somebody to raise your hand and tell me what do you think or what does your group think and why the answer is that one. Okay, I have David.
I think that the answer is B.
Why?
So, well, for like A, each time you want to get a grade, you have to go down to the object and go down to the grade again. So that's like 2 fetches to do that one or like many times. But for B,
yeah, but I think it's also the same for the object of arrays, right? Because you have to go to the homework and the homework itself is a 2-dimensional array. And if you know the structure of 2-dimensional array is actually also 2-point referencing, dereferencing, right? So this part is the same, right? So what's the main reason?
If that's the case, I'm actually not sure anymore.
Okay, so go back to this one, right? If I'm counting the homework, right? What's the access pattern of the homework in the left-hand side? Hello?
Is the pattern linear?
Is it linear? The left-hand side, is it linear? Well, somewhat of linear, right? But the thing is that you are going to access this one and go to this one and another one, right?
Yeah.
And for object of arrays, you are going to consecutively access the homework items. So which one would you imagine would use cache more efficiently?
I think the right would use cache more efficiently since it.
Right, because it's consecutive, and if you hatch the whole block is in there, right? Then you can imagine how low the cache hit miss rate is going to be, right? All right, thanks a lot. So the thing is like, in many cases, like if you go to like a Java class, software engineering class, they will tell you to do this. However, the right-hand side is actually more efficient in a lot of cases. So if you ever take like the database classes, right? The database in the background is actually implemented in the way like the right-hand side. So you think you are going to store your content like this, but actually most of the database, they will store your data in column store because for SQL queries, we select on columns, we judge the criteria on columns more often than all columns within a single record. So that's why column store is more efficient in this kind of workload. And that's why database systems, they embrace the idea of column store. So instead of using the one that you guys want, you guys learned from your other professors, but this is actually the most, a more efficient, a more efficient implementation as it's in use in many of the systems. All right. So another example that I want to give you is that, well, previously we have talked about this one, right? And we know the left-hand side has better CPI. So the first program, and now you probably know because the access pattern of the left-hand side is in favor of the fact we have cache. So even though both algorithms, they have exactly the same instruction count, the same clock rate, the same complexity. However, the CPI of the left-hand side is better because the cache access pattern is making it a higher hit rate. So by doing this, you by making the right-hand side code to be the left-hand side code, all you need to do is to interchange the order of the loop. So this is the very first technique called loop interchange. And the second one that I'm going to talk about is this, right? So previously we see, well, this pieces of code of AMD processor sucks, right? So, so you might think, well, AMD processor is a junk. However, it's not. It's just because the processor, the programmer who wrote the code didn't really know that this is the beast that you are interacting with. So if you look at this pieces of a code, it's equivalent to the previous pieces of a code. And can you tell me what's the cache miss rate for this pieces of a code after modification? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so given how divided are your answers, I would like to have you guys go to group discussion, and I believe I already sent out the questions through the chat. And again, please join your group as soon as you can. Otherwise, I would not giving you participation grades at all. And going into the breakout room is part of your participation. So I still see 3 of you here. For those 3 of you who haven't joined the breakout room, if you don't join, you will not receive any participation grade. You will not receive any participation grade. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, A and B, they are both popular answers. So can I have some of you share your thoughts? And you know, a lot of the cases, the most popular answers, they are not correct, right? So don't cheat, because your friends are definitely not going to give you the most insightful answers. All right, what do you think?
So I think the answer was A, because
Uh-huh.
most of the times, like no blocks would get evicted for each of the loops, and we have two-way associativity, so we would have CI and AI like stored in two blocks of the same set.
Right. So previously, you know, like the CI and AI, they all map to the same places, including BI, right? But right now, we separate them as two loops. So in the first iteration, we are only going to see the first time when we enter a new block for AI and CI, you are going to have a miss, right? And that's only compulsory miss. So that's 1/16. And the same thing for the second iteration is also 1/16. Right? So the answer here is this, right? The miss rate is only 6.22. If you can perform this optimization, code optimization called loop fission, right? So in contrast, so for AMD architecture, because it has very limited way associativity. So when you write a code like this, you have to know, well, if you are going to have data structure that you need to access within the same loop iteration, you have to think about how can I accommodate this stuff by separating them into different cache location, different loops, right? And this technique is called loop fission. In contrast, another idea called loop fusion. So this is actually a better fit for Intel processors, because for Intel processor, you have 8-way cache. So it means that within a set, you can actually accommodate up to 8 different data structure. And so if you have 4, why don't you just put them all together, and you don't have to separately create access for AIJ and BIJ, AIJ and CIJ here, right? So you can reduce the case of cache accesses, right? So for Intel processor, it's loop fusion, like combining 2 loops into 1 loop, would be a better idea. So you might be all confused, right? Like, okay, so what's the right thing to do? So the answer is that it depends on what processor you have. So previously, when we talk about instruction set architecture, we have a very strong plan saying that, well, with the abstraction of instruction set architecture, you don't have to worry about the lower level architecture. And yes or no. So in a certain degree, if it's not related to memory, and the answer is yes. However, for the memory part, because we don't have a unified structure, so it's really case by case. And for this example, we will see the same code works well on Intel processor, but not to AMD processor, and and you have to optimize the code separately. All right, so loop fusion, you do loop interchange, loop fission, that's one step. And now I'm going to talk about another algorithm called blocking algorithm. So the case study is matrix multiplication. And for those of you who are familiar with machine learning, you know the whole machine learning nowadays is based on matrix multiplication. When you are performing like the fully connected, when you are performing inferencing, when you are performing like a convolutional neural network, everything is about multiplication and accumulation, right? So matrix multiplication, I want to say, is probably the most important algorithm that you need to know now, right? And for your algorithm class, it tells you it's all the n cubic, right? So if I said for n equal to 1024, it takes about 1 second, you might imagine that, well, if I go to if I have the size scale up to scale up to like 2K, then you might imagine, because you size up by twice, so you should get like 8 times more time, right? So now I'm going to show you the demo. And let me see, the cache, okay, make clean, and then, okay, let me show you the code. This is the naive implementation. So this part is initialization, and I have a function called mmabc. And if you don't go into the code of mmabc, it's actually implementing the naive matrix multiplication, which is the uncubical library, uncubical implementation. So right now let's compile it. And as you can see, I already used -03 here, which means that the binary is highly optimized for the compiler, by the compiler. So now let's do like mn 1024. So as you can see, it's indeed 1 second. However, for 2048, because it's an uncubical algorithm and we double the size by twice. So you might imagine it would be 2 to the cubic. That will be 8 times more. So suppose we should see our result in 8 seconds, right? However, I believe we should spend more than 8 seconds now, but we still haven't got our result. So there might be something wrong going there. Is the program going to finish? Okay, the answer is that yes, the program finished, but it needs like 28.5 seconds, right? So that's not efficient. So what's wrong with that? So one thing, right? So now let me show you this, right? So the reason is because if you analyze the behavior of matrix multiplication, and let's say like if each dimension is 2048, and each row would take, and if you are using a double floating point, each row would take about 16 kilobyte of space, right? And the processor that I'm using here is actually an Intel processor, and its cache architecture is, so this is a Core i5, but it's not too different from Core i7. So its first level cache is indeed 32 kilobyte, 8-way, 64 byte blocks. So the total L1 cache capacity is only 32 kilobyte. However, each row would take about 16 kilobyte. And thinking about your algorithm looks like this. So the pattern would be, if I want to get the result of C, first of all, I need a whole row of A and a whole column of B. And that's already 32 kilobytes. And plus, you need a space for C as well, right? So definitely the capacity needs would be an issue, right? And the other thing is that, okay, even though that set the C aside, just look at it A and B, because the next thing you are going to do is not reusing this column. You are going to use another column in B. So right now, you are going to kick out one column and this column will be accommodated. And then the next time you are going to have, you still need another column. So this part is always a miss, right? And it's very unlikely the whole column is going to be the cache because it will be kicked out. So even though you might argue, well, in the next run, I'm going to see the same column again, but unfortunately, it's definitely going to be kicked out after we calculated C, right? So this is not going to work, right? So and if you want to see how bad the miss rate of that is, there's a good tool. Well, I don't think wget. Sorry, get Valgrind. There's a good tool called Valgrind that would help you to. Some of you might already know this tool because it's a really common tool to detect memory leaks. However, this is also a good tool that you can use to identify how many cache misses that you have in the pieces of a code that you run. So the command line is pretty simple. You just run valgrind -tool cache grind, and right now I'm just showing you the 1024 configuration, because even for the 1024, it's already very. It takes a long time to profile because the profile actually did a lot of work in the background to collect those information. Right, so that's the Okay, so let's do that. And there's another way that you can use Intel's performance counter monitor, like on Windows, on Linux, they do have this tool installed. So, but right now I'm going to tell you a better algorithm. In the meantime, when we wait for the Valgrind result to come out, right? So for the block algorithm for matrix multiplication, so what I'm showing right now is the default naive implementation, and this is the block algorithm. Wow, it has 6 levels of loops. You might feel crazy about it, and you start to doubt how does that work, right? So I just give you some high-level idea, and if you are interested, go inside and dig into the code. You will figure out what it basically does is this. So when I calculate the CII and CJJ, CII and JJ, instead of each time I fetch the whole row and the whole column, I just look at part of the row and part of the column, and I just do the partial sum for C. So and then the next item I'm going to is going to still be within a sub block of B, right? And when I go to the, and instead of now going over the boundary of a sub block, I just calculate the next row in a sub block of C. And in this way, you will see like each time I only touch a subset of the columns in B, a subset of column of rows in A. So you are basically partition the computation into sub-block. And every time you just upgrade the partial sum in C for each sub-block multiplication and accumulation. Right, so in this way, you can imagine, because I only need to store this sub-block, and if this sub-block size is controlled in a way that is under the cache size. So for example, if you have a 32 kilobyte cache, right, you have to make sure that each time your sub-block is probably less than 8 kilobyte, right? And for 8 kilobyte, you can imagine, well, the sub-block should be better for, well, should be less than 1024, right? However, if you have a 2K block and if you don't maintain the size to be 1024, then you know, like for each sub-block, it's going crazy, right? So that's why block algorithm will work. Okay, so on the other hand, let's go back and look at, okay, so now for the MN 1024, you can see the IL1 cache miss rate is almost 0 because we are just reusing the same pieces of code again and again, right? So except for fetching the 900 instructions in a cache, they are mostly hit. However, for data cache, the miss rate is about 24 to 25 if you have a 1024 size of array. Right, so now let me show you, I have the code called block MM, right? So if I run block MM for, previously it takes about 30 seconds to finish the matrix multiplication. But right now, if I set the n to be 128, see, it only takes about 6 seconds to finish the whole matrix multiplication. It's a lot faster than the non-block algorithm version of the matrix multiplication code, right? So now let's try to use the Valgrind to see if the cache performance is really indeed improved. So because of the time, I would just make the array smaller, because just the smaller array is still faster, right? So if you look at the matrix multiplication or block matrix multiplication, it does help improve the cache miss rate of the matrix multiplication, because each time will only operate on a submatrix, right? So now I do want to invite you to think what kind of misses can be improved in block algorithm. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let me see. This is what you guys think. Let me send out the questions through group chat real quick. But in the meantime, right? Okay, so Valgrind does finish profiling the block algorithm, and as you can see from the block algorithm, the cache miss rate is only 1.1% now, right? Comparing against the non-blocking algorithm, which takes about like 23%, right? So you can see the significant performance improvements is indeed coming from the improvement of cache misses, right? But what's the source of the cache misses? Why don't you go ahead and discuss with your friend in another 2 minutes? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, looks like after discussion, more of you think it's D, both capacity and conflict miss. And the second popular answer are B or C, right? The capacity miss and conflict miss, right? So at least some of you are, at least most of you are agreeing with like either capacity miss or conflict misses. So right now, I do want some of you to share why do you think there are such misses can be improved in by block algorithm? Okay, I have Anwar.
Yeah, basically, because we can partition the matrix up like this, that we can make use of the like L1 caches like blocks, without having like repeat addresses and all of that, and that handles like capacity too, because we're not repeatedly trying to fit everything into like this one set or one block, for example. At least that's how I understand it in general.
You're right. So the big thing here is that, right now, when I do block algorithm, right, the footprint is only now within a subblock, right? So you can just make sure the subblock is fitting in the cache size. So you won't, and every time when you're done with it, you don't reuse, you don't need to go back and revisit the subblock because you have done everything you need for the subblock. So you can reduce the memory usage, right? And the other thing is that because you don't have the case that previously I used the raw, but because I don't have space, so I kick it out, right? So you can also potentially reduce the case of conflict misses, right? So that's why for this question, the answer would be D, because both of the capacity miss and conflict misses, they could be addressed by the block algorithm. Okay, so finally, I want to give you one more example. So previously we talked about you could add. So previously we said, right, we said instruction count is really important. So we want to produce the code that is shorter. However, through the sorting example, you know, sometimes longer code doesn't mean the performance is worse. So for this matrix multiplication example, let me tell you one. Let me give you one example, the matrix transpose, right? So if I transpose the matrix and then I instead compute on the original matrix, but I do block algorithm on transpose matrix, and I do need to pay the overhead of transposition. So if you look at the block mn transpose.c, I do have additional pieces of a code that performs the transpose here, right? So right now, let's time it and let's do block mn transpose still 24, 1024, and let's see like 2048, right? And let's see, we still use the same n, and see it's again faster, right? Previously, it still takes about 6 to 7 seconds, but right now it's going down to 5 seconds. So this gives you another counter example, like, okay, I add some complexity or add some more operation into the code. However, the rest part of the code is going to be more smoothly. But I also want you to think through this question, but because we are out of time, so we are going to stop here today. And but do make this a homework that you think through by your own. But before you leave the classroom, several things. Reading quiz is due tomorrow. Assignment 4 is up on the website, and in assignment 4, we are going to ask you something about matrix transpose. And other than that, enjoy the rest of your day, and we might be, if you are planning to attend the lab lecture, I will see you in 40 minutes.
I guess I just feel like, I guess I just feel like nobody's honest, nobody's true, everyone's lying.